and welcome to another wonderful day of physical chemistry. So today we're going to take what we now know about the behavior of particles trapped in a well and use it to actually kind of get into the idea of spectroscopy. So we're going to start by looking specifically at vibrational spectroscopy. So one of the big things I want to start by emphasizing is really how spectroscopy works. So essentially, the reason why spectroscopy works is because energy levels are quantized. And so you can focus on is trying to find a specific wavelength of light that that a molecule will either absorb or release when it relaxes down an energy level. So we're going to be focusing more specifically right now on absorption spectroscopy. So in this case, I have a molecule that's going to be excited from a lower energy state up to a higher energy state. Now, one of the important things to realize is that there is a wide variety of types of spectroscopy, and essentially they're characterized by two key features. First of which is going to be the energy in which the energy separation between the levels, and the second of which is what type of motion I'm exciting. So we're going to divide our treatment into three key regions, again, each of which is characterized by a certain energy regime and a certain type of movement that results. So the first of which is rotational spectroscopy, which we'll talk about more in a couple of lectures. And so what we're measuring here is going to be changes in rotational speed of a molecule. So essentially how fast it rotates. And these tend to be fairly tightly packed spectra with a lot of excitations, typically on the order of about 1 centimeter or about 0.01 kilojoules per mole. So very mild separations. We're going to be focusing here a little bit more on vibrational changes. So these are going to measure rates in changes in the rate of the vibrational movement that we brought up previously last time with the harmonic oscillator. And these typically occupy the infrared region, and they have typical wavelengths somewhere on the order of about 10 micrometers. And again, these have energy separations about 10 kilojoule per mole. So not huge, but turns out to be fairly significant. And much later in the semester, we're going to be talking about electronic excitations. So this is what you may typically think of when you're thinking of spectroscopy. These tend to use the UV-Vis spectra, and we're actually moving an electron in between one orbital and the next. And these are somewhere on the order of hundreds of nanometers. So somewhere in between about 100 and 10 nanometers if I'm exciting from a core electron orbital, all the way up into, say, 1,000 nanometers if I'm talking about excitations between long conjugated chains. However, we're going to be focusing specifically here on our vibrational spectra. So what we're really looking at with vibrational spectra is going to be the movement of electrons in a potential well. So essentially this well is going to extend from zero, where the two atoms are essentially sitting right on top of here, out to infinity, where they've been completely disassociated. And it turns out that the real description of the potential has, again, a sharp wall at low distances, because again, I can only compress two molecules so well, but it actually has this big long tail at larger distances. And so this is where we start having, as I put more energy in the system, it gets closer and closer to disassociation. At a certain critical threshold, we'd go from a bound molecule to a completely disassociated molecule where it has enough energy to escape from our well. Now, as with most things, it turns out we can describe this potential well using a Taylor series. So we're going to have our first term, which essentially says how deep our well is. So this is going to be our 0-point potential, because we're going to set our x value of 0 for the equilibrium bond length. Then we're going to have a first derivative of the potential with respect to x. And then we're going to have a second derivative and so forth. Now, what we can do is say, all right, this first term is essentially how deep we are. We can artificially choose whatever zero we want. So we're going to set essentially the bottom of the well to be 0. This first derivative term, well, it turns out this is a minima. And the first derivative of any minima or maxima is going to be 0. So that's actually fairly easy. And then we're going to ignore any higher order terms, so third or fourth order. Again, another classic physics trick. So this means that we aren't going to we're going to do a very poor description of the potential far away from the bottom of the well. But by focusing in on this second order term, we're going to actually do a pretty decent job of describing systems that are fairly close to this equilibrium bond distance. Well, lo and behold, this remaining potential term should look fairly familiar. It's a quadratic dependence on position and 1/2 times a constant. Oh yeah, that's the harmonic oscillator. So this is essentially the same term we brought up last time. But again, the big take home here is that it turns out that our force constant is actually going to be the same as the second derivative of the potential at this equilibrium bond distance. So it's another way to try and arrive at the force constant for a harmonic oscillator. And as we addressed previously, this is going to produce energy levels of the vibrational quantum number plus 1/2 times h bar omega, where again, omega here is the vibrational frequency, which is going to depend on our force constant, our second derivative, and the reduced mass of the system. However, this just focuses on the system, the structure of the system itself, as well as the energy levels. So we're going to be focusing a little bit more on this harmonic oscillator, and now we're going to focus a little bit more on energy separation, because we want to know what photons we can absorb. And here comes an actual pesky little issue, is that it turns out when a photon is absorbed, it brings along a certain amount of movement with it. So this means that when I absorb a photon, I'm going to have to essentially excite an energy level. But because of the nature of photons and particles, which we'll talk about more later, only certain transitions are going to be allowed. And it turns out they only bring enough movement to essentially excite a single vibrational level. So they can only go from, say, the 0 state to the 1 state. So for all photon absorption and release, we can only have a change of our vibrational quantum number of plus or minus 1. So you can imagine when you absorb a photon, it's possible. The most likely case is I bring in energy and I bounce up as I essentially reinforce the movement. But it's entirely possible that you can have the photon come in the reverse counter to the movement and cause the vibrational level to drop by a single value. However, all that extra energy has to go somewhere. So you're typically only going to see a decrease in vibrational levels during electronic spectroscopy, where we have a lot more energy coming along for the ride. So for practical purposes, in infrared spectroscopy, where the only excitations are really vibrational ones, we're only going to see an increase in vibrational levels. So we're only going to go from 0 to 1, or 1 to 2, or 2 to 3. So we're only ever going to go up. Now we're going to bring in a key feature of quantum mechanics, or statistical mechanics. And that's the fact that it turns out for most vibrations above about 500 inverse centimeter, we're only really going to find the ground state occupied. Because again, remember, at room temperatures, I can only, my molecule is only going to be able to jump up so far due to thermal features. And it turns out that cutoff is somewhere in between 300 to 500. So this means for most vibrations, if you remember your infrared spectroscopy that we're interested in, most of our vibrations that we care about are above 500. So this means that in most cases, we're only going to be occupying the ground state. So our dominant excitation we're going to see in IR is from the ground state to the first excited state. And because of this, we're going to have a discrete separation between these levels of pretty much h bar omega. And as a result, we're going to have very sharp peaks because that's going to be the only absorption really taking place. Each bond will absorb a photon at a different characteristic frequency. And because we're only seeing 0 to 1 transitions, we're going to have a series of fairly sharp peaks. Now, it is worth noting that this does break down under the low energy side of your infrared spectra, which is one of several reasons why once you get below 1,000, our spectra gets a little bit messy. But as we get to higher wave numbers, we tend to have, again, very sharp peaks, which is one of the reasons why IR spectra is so useful. And again, this is most apparent in organic spectra, where a lot of our frequencies are, say, around 1,200 to 1,500 for a lot of single bond stretches. Double bond stretches go from about 15 to, say, 2,000 wave numbers. And then once you get up into 3,000 wave numbers, you're often dealing with hydrogen stretches. And again, most of these are going to be very characteristic because we only have a single excitation we're dealing with. So we can, again, provide the energy for each of these vibrational levels as the energy equaling the vibrational state plus 1/2 h bar omega. So for the ground state, this is just going to be 1/2 h bar omega. And for the first excited state, it's going to be 3/2 h bar omega. Now, one of the unfortunate parts when we go to spectroscopy is we're going to care a little bit less about the energy of these excitations. And it turns out, especially when we're talking about infrared spectroscopy, most of the results are presented in wave numbers. So we go ahead and essentially flip around the units. So we're going to be looking at the energy in terms of wave numbers, which we give by this vibrational term G, in terms of the vibrational quantum number, again, our classic half value correction, and what's called the vibrational constant. So our vibrational constant is simply going to be converting our h bar omega into terms of wave numbers. So again, not too surprisingly, we're going to see the h cancel from the transition from energy into wave numbers. And we're going to see our omega terms still show up. But again, we're left with the 2 pi from the h bar and this c for a unit conversion as we go from energy into wave numbers. So again, this vibrational constant is usually what you can think of having measured most of the time when you're taking infrared spectroscopy. And one of the reasons why is because our only major absorptions are taking place when we go from when we increase our vibrational quantum number by 1. This results in an energy separation in between levels of essentially just our vibrational constant. And this, again, really helps emphasize that even if I do have a few molecules up in this first excited state, they're still going to tend to have the same absorb light at the same wave number. And so this is, again, another reason why we see such clean peaks in infrared spectroscopy. And it is worth noting that this is going to be the harmonic oscillators predicting all of our vibrational excitations with this same energy based on our vibrational constant and clean peaks. Well, it turns out that this isn't always going to be the case. And one of the reasons why is because, remember, when we started with the approximation of the harmonic oscillator, we assumed that we weren't moving too far away from our equilibrium bond distance. We didn't move too far away from an x of 0. However, that's actually pretty true when you're talking about your ground state and your first excited state. But by the time you get to second, third, fourth excited states, well, that's no longer quite so true. So to fully describe those systems, we're going to need a much better potential. We're going to do that next time as we bring up our new friend, the Morse potential. Until then, take care.